Okay.
I forgot my. Yeah. I was wondering, like, so white.
So what I thought we would do is just go over the questions that are in the practice exam. Those questions.
Awesome. Thank you so much. Yeah.
Those questions will cover a lot of what's going to be on, on the final, on the actual exam. There will be some more, and I already gave you guys some hints that it will be on. But it's only on the nuclear section. And if you think about it, if you look at the whole nuclear section, I know I gave you guys the slide set last night. Where, I said from page 447 all the way up to 700 something. But if you look at it in totality, you see there's actually not that much. It's just I repeated a lot of slides because if I'm repeating, it usually means it's important. And also because when we go from one lecture to the next lecture, always give a little bit of an introduction, a little bit of a review. So you'll find some slides being repeated. But if you look at the totality of everything, the whole physics section is actually a lot, but I really focus on some of the physics here that I want you to get, which you probably wouldn't, it's not really in textbooks, that's really why. So let's go through the questions. Did you guys find the practice exam difficult?
Not so much, but it's fair.
Another hint. I always basically often do this. Put almost the answer in the question itself. I don't know if you guys have noticed that. That's a deliberate way that we're writing these questions. So an example of that is, or again, no trick questions. I don't ask trick questions. I don't like to do that. Okay? Why I say that is because if you look at question 3, which was, there are 2 grades of plutonium, weapons grade and reactor grade. Or weapons grade has a dash in between. And reactor grade. Circle the one which is best for developing nuclear weapons. It's obvious, right?
It's obvious, yeah.
So the question is, the answer is in the question itself, essentially. That's but because people often think, I asked this question before on the actual final, because people often think that I'm asking a trick question, they don't answer they don't get the right answer. But the answer there is obviously weapons grade. Right? That's really important, I think. Okay, so let's go to the first question. So fill in the blanks in order of the sentence. In blah, 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 the proportion of blah, blah, blah is increased in a sample by physically removing which atoms. So I had 4 different options there. Conditioning, which is, we haven't even talked about conditioning yet. And U238, U235. Enrichment. And if I'm saying here it's increased, the proportion of some atom is increased, then you know that it's not going to be what? You know it's going to be. It's going to be enriching. Right? You're increasing something. But then you have to know what are you actually enriching? What are you increasing? It depends on different circumstances. But in this case, we're talking uranium enrichment. So which one is it?
B.
B. Right. You're enriching U235 with respect to all the other uranium isotopes. And generally, in natural uranium, it's going to be, mostly uranium-238, 0.3% uranium-238, and 0.7% is uranium-235. You guys know that. Great. So the next question is, what is the approximate half-life of cesium-137 and strontium-90? C. C, exactly. 30 years. 30 years. The 2 are different. The one is 28, the other one is 29.5 or something like this. But that's not really the important thing here, is it? It's that it's 30 years. For a very long time, it stays radioactive. So if this stuff, gets into the air and then settles down into the ground. Actually, this stuff first comes off as xenon gas, and then it changes into cesium, right? That's another concern, right? It's a gas, it goes up like this, and then becomes cesium, and then becomes a metal which sticks in the ground. So it's a big issue for things like if a nuclear power plant has an incident or something like this. So the next one I already went through. There are two grades of plutonium, weapons grade and reactor grade. Circle the one which is best for developing nuclear weapons. Again, no trick questions, it's just weapons grade. Now, from the point of view of a terrorist, describe the advantages and disadvantages of the two fissile materials. And then I had HEU, and I had easy to produce, right? So first of all, what are the two fissile materials that I'm talking about?
Plutonium and
Yeah. And really here I'm talking about uranium-235. But if you say HEU, that's, like I have here, that's fine. Plutonium, you say just PU, that's fine too. Remember, you can make nuclear weapons out of any grade of plutonium. But weapons grade is desired for making nuclear weapons. So what's the advantage of HEU?
no test needed.
Mm-hmm. It's another advantage of using HEU. If there's no tests needed, that's the main one. It's also easy to manufacture and to know. It's easier. What's the disadvantage? Hard to do, hard to get, hard to finish. Exactly. You'd have to steal it, right? Or you'd have to make it, produce it, which is hard. As you see with Iran. So the other fissile material is plutonium, right? The advantage is it's easy to produce. How do you produce plutonium?
From the way we processing.
Yeah, but how is it produced? Where's plutonium come from?
U238.
Who said that? Uranium-238? So what happens?
It fissions, or no, it decays into.
Right, so it captures a neutron, and it goes through a series of decays and becomes plutonium-239. Right? So it's a fertile material. It's not fissile, it's fertile. It will become fissile once it's captured a neutron, and then it decays into a few more times, and then it becomes pure plutonium-239. And about 1 to 2% of fuel itself is going to be plutonium. Hello? So, just 1 second. I want to say. So it's easy to make in a reactor, right? Because it captures a neutron. That's the important thing. It captures a neutron. It's not fission in this case. It just captures a neutron, and it becomes uranium-239, or sorry, uranium-239, and then that decays several times, and then plutonium-239. It's very easy to produce. What are the disadvantages with plutonium? Right. Can you make a gun-type weapon out of? No. Why is that?
Too much neutron. Too many neutrons.
Very good. Too many neutrons. Too many neutrons. So once it brings together, it's basically disassembling itself. You can't do it fast enough. So that's why you need to do it this way with this implosion mechanism, where it's much faster. Right? Good. So, and the disadvantage then? Yeah.
For terrorists.
No, just, yeah.
In general.
In general.
We have to test that.
Exactly. You have to test it. Is anybody going to the CTBTO during the summer? Yeah, I mean, that's right. You need to test it, and that's really the big difference. Not easy to make a bomb either. So, why is it necessary? This is question 5. Why is it necessary to cool a reactor even after it's been turned off and it's not sustaining a chain reaction? So what happens? Right? Reactor is turned off. There's some emergency. Big earthquake. Reactor turns off abruptly. Scram. Let's go scram situation. Right? Why is it still a problem?
Because the reaction doesn't stop right away.
Which reaction? The chain reaction stopped.
Yeah, the chain reaction is stopped, but
Uh-huh.
the process through which the various pieces of material continue
Decay.
to decay.
Excellent. Yes. So it still has decay heat, and that decay heat persists for a long time afterwards. Do you guys remember that in my slides I showed it was almost like an exponential decay? So you saw how the power changed as a function of time, and even after 1 minute, it's still like running at so many percent, 4% or something like this, your reactor. So that's the important thing. It's as if the reactor is still on. It's still producing decay. Things are still decaying, right? So that's the problem. And that's why you need to constantly cool the reactor, even though the reactor's off, right? Reactor's turned off. But it doesn't really turn off. There's this internal heat that's heating the water, and if you're not cooling it, that water is just going to evaporate, and so the fuel itself is going to start to burn and melt and all. You guys know about that scenario. Okay? So decay heat. So as I say here in the answer, is that the spent nuclear fuel remains hot because of decay heat produced by decay of the isotopes produced in the reactor. Okay. So question 6. What can be expected as the reactor fuel exposure time to the neutron flux is increased, and why is that important? A, B, C, and D. You guys have the questions in front of you, right? Which one? This is really important.
A?
Why would you say A?
I don't remember why, but I remember studying that's the case. That the more you leave a rod inside, that actually less is usable for weapon purposes. I don't remember the specifics.
Did I make a mistake?
And then you say that you decrease and then the force
Oh, sorry,
is less
sorry.
useful.
So not A, but B. Right? So the ratio of plutonium
Oh.
to 40 increases, and that makes it less useful for nuclear weapons. Okay? That's the difference between less useful. Doesn't mean it's not useful for nuclear weapons. That's the difference between reactor grade and weapons grade. You guys see what I mean? It's the plutonium 240 that you're producing. How are you producing plutonium 240, by the way? Somebody at the back of the...
So, I said by blending neutrons into
Right. So the plutonium-239 captures neutrons. So plutonium-239 that's being produced captures a neutron, becomes what? 1 neutron plus plutonium-239 becomes plutonium-240, right? Neutron, you're not changing the element. That's a question later on, I think, right? The protons tag the element. You're not changing the element. You're adding neutrons. You're changing the isotope. So it becomes 239 to 240. You guys follow what I'm saying? Yeah. So the difference between uranium-235 and uranium-238, they still both have 92 protons, right? But the difference is that they have 3 more neutrons in the case of 238 compared to uranium-235. It's the neutrons that change for the isotope. Okay? That's really important. So plutonium-239 captures a neutron, and then that 239 becomes 240 with 1 more neutron. If I change it by a proton, then it would be a completely different element. But here I'm changing it by a neutron. And in a reactor, you have this high flux of neutrons everywhere. Right? So it's bound to happen that the plutonium-239 is going to capture a neutron, and it's going to become plutonium-240. And then it's bound to happen that plutonium-240 is going to capture another neutron and become plutonium-241. And that's bound to happen from the plutonium-242. So you can see how you get all these funny isotopes being produced in the reactor itself. And generally, it's the odd isotopes that are better for producing nuclear weapons than even isotopes. So the answer is B, right? The ratio of plutonium-240 compared to plutonium-239 will increase, and it will be less useful for nuclear weapons. right? Harder to build a weapon out of. Doesn't mean you can't build nuclear weapons, because you can make weapons out of any grade of plutonium. Okay, so I kind of gave the answer to 7 already, but let's go here. So, how do we define an element? The number of which nucleon? What differs in an isotope of an element? The number of which nucleon? Which nucleon is neutral? So, A. How do we define an element? Yeah, number of protons. I gave the answer. What differs in the isotope of an element? I gave the answer there too. Neutrons, yes. Which nucleon is neutral?
Neutron?
Neutron, yeah. Kind of makes sense, right? Neutron, neutral. There's a reason why that quite studied. And I think in Italian, it means neutral, right? Neutron.
That's Latin.
And it's Latin.
Latin is neutral.
Is it?
Neutral.
Neutral. You can guess what it's going to be. Okay, so 8. Circle which of the 4 diagrams below most resembles a PWR. This was a type of reactor that was so severely affected by the Japanese earthquake and tsunami in 2011. You guys remember the difference between a PWR? What's a PWR, by the way? Good. And BWR? Very good. The answer is in the question. What's a BWR? What's a BWR? What's the difference?
They run some steam more than just water in the liquid state.
Right. But if you think about the word boiling water reactor, think of it as being directly boiling the water, producing steam directly through the turbine, as opposed to a pressurized water reactor. Right? Pressurized water reactor, you have that extra loop. Right? So if you look at those pictures, first of all, I'm deliberately, did I hear or not? Oh yeah, the very last, there's a part where I say gas, which is the first one. Right? There's no gases involved. That's another type of reactor. There's one, that's the 4th picture. I also have gas. That's another type of reactor. We're not talking about that type of reactor. So you only have really 2 choices here. Right? So which one do you think it is? Directly boiling.
So we'll read the first one, right?
Yeah, exactly. Right? It's one loop. It goes, you're going straight through the turbine. Water is boiled, producing steam, goes straight through the turbine, and then gets cooled, and becomes water again, and then goes through, and so on. Whereas the pressurized water reactor, you have an extra loop, right? And you're isolating the one loop from the other loop. And you may remember, I don't know if I had a detailed discussion about Fukushima, but it's one of my concerns about boiling water reactors is that whatever radioactivity you have from the fuel itself, right? Fuel is not perfect. There's always going to be dust and stuff, particulates that go into the water, and so it goes straight into the turbine. So the turbine is itself radioactive. So that's another level that I worry about. And I believe in Fukushima the control room was close to where the turbine building was, or it was in the turbine building or something like this. So that's another worry that I have. Okay, so let's go to question 9. Without prior knowledge, a person was exposed to unknown unsealed source. List 3 principal ways, I call them pathways, that this person can be exposed to radiologic materials. And usually, when I ask this question, I'm really flexible about what your answer is going to be. It's just common sense, really. But there are 3 proper ways of saying it. What are 3 ways that you could get affected by radioactivity, essentially? That's what I'm asking.
Well, can go for your skin.
Mm-hmm. So that would be direct exposure. Mm-hmm.
You can inhale it if it's particulated, or you can ingest it if it's...
There you go. There are your 3 answers. Right? The answer is really in the question itself. That's what I was thinking, right? But that's very, very important. And later on, I'm going to talk about it a little bit more in an extra question.
So what did he say for the third one?
So it's ingestion, inhalation, and direct exposure. Okay? So, what is meant by the linear, again, the answer is in the question. What is meant by the linear no threshold model of exposure to low radiation doses? You guys remember this was in the video? Okay, I'm not going to continue. Somebody else knows. Linear no threshold model.
Isn't it that like there's no threshold for radiation exposure because they can't quite tell at what exact
Excellent,
point?
Ruby, excellent.
Yes, sir.
That's the point, right? There is no threshold for radiation. The way you can think of it is this way, and it's very important. So, this is the effect. So the number of cancers, whatever the effect is going to be, and this is dose. Now, what they had is they know how many cancers, and but the effect was high doses from studying, the people in Hiroshima and Nagasaki and these kinds of incidents. So you have that right at the top. Right. You know that at 0 dose, and what would you expect for an effect?
For 0 dose,
For 0 dose.
nothing.
Exactly. Here, this is the region where people are living close to nuclear power plants. Right. But cancer, the effect is so difficult statistically to measure unless you have something very rare, like a particular rare cancer or something like this. And people get cancer all the time. So it's impossible to measure, almost impossible, unless you have very rare cancers, to measure in this area whether the effect is due to radiation or some other environmental causes or whatever the cause is going to be. Right? So what people do, they draw a straight line. Just like this. They draw a straight line. And that way, they can have a sense of the risk of radiation to people living, that are exposed to low levels of radiation. So it's called linear no threshold effect model. Okay. And this is what most regulators, almost all regulators, apply as their model. But we don't really know if it's right. So a lot of people say that it could be something like this. Other people say that there's evidence that it's like this, so that people living on high mountain tops, where you're constantly getting cosmic rays, for example, different kinds of radiation, they seem to have lower risk of cancer. But that could be environmental. It doesn't mean that it could have nothing to do with radiation. But some people are saying that it goes like this instead of going like this or like this. It's very, very difficult to measure at these low doses. And that's why what people consider to be the most prudent thing is just to say, well, we know this point, and we know this point, this data here, so why not just draw a straight line?
So it's a statistical
Yes.
method.
It's a statistical method, and there's actually a relationship that you can have given on the dose. You can figure out over a population how many people will get certain types of cancer. These are the kind of estimates that people do, when there's a very serious incident like Fukushima, when they have a sense of how much radiation, how much radioactive material people were exposed to, like a cloud moving, and they do these kinds of calculations to try to figure out what the effect was on the population. But we really don't know. But it seems like a proven thing to do, and this is what almost all regulators, I think all regulators use. Linear no threshold model. So it's really, really important. There is no threshold for radiation. In the video, I talk about this a bit more, but you guys can have a look at it. This is really important. That's why I emphasize it here. Is there any questions about that? You guys can see how this is important, right? I could ask a question about the linear no threshold model because it is so important. So the agreement between Iran, this is question 11, The agreement between Iran and the P5+1 has essentially frozen the Iranian nuclear program in return for reduced sanctions. One of the, we don't have the reduced sanctions yet, in detail yet, okay. One of the important concessions that Iran has made is to downblend the stockpile of 20% enriched UF6 to less than 5%. Can you explain what the reason is why 5% is more acceptable to the international community than 20%?
It's the concept of breakthrough. So with the 5% more time is required if the decision is made to get to that.
Good, yes, exactly. And do you guys have a sense of what that is, the difference between 20% and 5%? I say that in the Iran panel discussion, which I really want you guys to see. Because I
You
might
explained the running marathon. Yeah. Where-
Very good.
Where you said if you win 5%, you're like 18% ahead, and I can't remember what the number is.
I have another example here,
Yeah.
which is the, I was going to have a picture. Anyway, that's okay. You can picture getting to weapons grade as like eating a bowl of sushi of 10 pieces. Okay? So if you finished not bowl, a plate of sushi, if you finished the plate of sushi of 10 pieces, then you've gotten to weapons grade. Okay? How many pieces do you think you've eaten when you've gotten to 5%? 5%. 5% enrichment.
7.
7. Yes, exactly. And 20%? Did you take a guess?
Yes.
Wow. You're right. It's 7 pieces. But that's already amazing, right? Because you have to realize it's not linear, right? You go from 0.7% to 90%. It's not linear. And you were right about 20%. If you're getting to 20%, that's eating 9 of the pieces. Only need to eat 1 more piece, and then you're there. Isn't that striking? It's really astonishing to me, right? So that's the reason. And if I can think of one important thing that you learn out of this class, it's that. I mean, in terms of the concern that we have with that material. And that's just because of the enrichment process itself. And if you think about it, do you remember we did this little experiment with the, may not have done it in reality, the chocolates? Did I do that with you guys? I've done it in another class. Right? We start out with, it's 0.7% uranium-235 compared to uranium-238, right? Essentially, there's two isotopes. So that's the same as saying about 7 uranium-235 marbles, and the rest is going to be, the rest of the 1,000 is going to be uranium-238. If you get the 5%, what's 5% of 1,000? 50, right? So, do I need to show you guys? I'll show you guys. I think it's better if I show you. I won't do this. You guys know I put the lecture set online, right? But we're not covering the whole thing, only half of it. Okay, just 1 second. I think we are there. This is the example that I used, right? population. So we start with 175 kilograms of natural uranium. Remember, natural uranium was 0.7% uranium-235. The rest is basically uranium-238. Right? And we want to produce 1 kilogram of 90% weapons grade, essentially, weapons grade uranium. It requires 227 SWU. Remember its unit SWU? Right, separative word unit. It's an important word. Now, if I start with 175 kilograms and I enrich it at 4.5%, not even 5%, like 4.5%, I produce this much material. That requires 160.6 SWU. This SWU is basically the effort that you need to do to enrich it. Right? Basically the work that you need to do. 7% of the work is done in this first step. The next step is taking this 20.8 kilograms and then enriching it further to this 90%. That's only 66.4 SWU more, or 30% less work. That's where this analogy comes from with the sushi. You guys get what I'm saying?
Mm-hmm.
So, how can this be? It's kind of counterintuitive, right? But really, it's not. So I usually do this with you know, when it's Halloween. This time it wasn't, and I bring in candy and stuff like this, and do
Mhm.
more candy and stuff like this. But not this time. Let's see how this is done. If we have 0.7% uranium-235, right? That's 7 uranium-235 here, right? The rest, 993, is going to be uranium-238. You guys get that, right? That's 0.7%. So 1,000 marbles or 1,000 candy. If I get the 5%, remember I'm enriching, right? I'm not producing the uranium-235. I'm taking uranium-238 away, essentially. Then the fraction I need to have is 7 divided by 140. That's going to give me 5%. Okay? So that means that in that first step, I have to go from 993 U-238s down to 133. Right? And that's the major work that I have to do. Then the next step, right? I have to pull out 860 of them. So large work is done. The first jump. Then the next step is to get to 90%, right? Well, what's 90%? Well, 7 divided by 8, essentially, is 90, close to 90. And that jump is only pulling 132 of them away to get to this. So first, to get to 5%, 4.5%, I have to remove 860 of them, which is a lot of work. Just think of somebody going into the, grabbing the U-238s like this. That's why I usually do it, and I bring a bowl and people pick out these things. Right? It's a lot of work. And then the last step, to go from 5% to 90%, is only pulling 132 more out. Right? So it seemed counterintuitive, but if you really think about it, it actually makes sense. And that's why we're so concerned about enrichment in general. Does that make sense? So if it doesn't make sense, go home and try it and think about this, because this is a really important point that I want you guys to understand. All right. So, yes. So next one, what are the nuclei produced after fission called? Which one? You guys know? A, B, C, or D? Fission products.
Products, yeah.
Right. The answer is in the question. Is that what it's saying? There's no trick questions. Right? But that's important. That's what they're called, fission products.
Yeah.
Right. Are those fissile? What happens to these U-235s and things that split? What would they break into? These fission products. What do they look like? Will they fission themselves after they fission? No, they split in half. Listen, they don't split in half. But they can split in half, right? But then they're far from the actinides, which is that the bottom part of the periodic table, right? You're not producing fissile material through this process. You're just producing fission products, things like radioactive cesium-137, strontium-90, all these radioactive metals and things like that, or gold, or platinum, these kinds of things, is what you would produce. But not fissile materials that you could produce for reactors. Not that way. Okay, so those are fission products. Next question. If I had 8 kilograms of cesium-137 and strontium-90, how much would I approximately have left in 90 years?
2 kilograms.
2 kilograms. Why?
Because for the CS137 and CR90, decay times 30 years,
Mhm.
and we have 8 kilograms.
Mm-hmm.
So it's gonna split like first time 8 kilograms, you're gonna have remaining of 4,
Mm-hmm.
and then we need 30 more years, and then we're gonna have 2.
Mm-hmm.
That's what we're gonna have.
Yeah.
So 3 plus 30 is 30.
But you say.
Isn't it-
Sorry. Yeah, you're right. It's 1.
Uh,
Right? So you start with 8,
yeah,
then becomes 4. That's after 30 years.
yeah.
Then becomes 2 after another 30 years, which is 60 years. And then becomes 1
Oh, yeah,
after another
yeah,
30 years.
that's
You're
true.
splitting half each time. So I said in a couple of sentences, explain how a nuclear weapon and a dirty bomb are different. What else is different about it? What does it mean there's no nuclear explosion?
Well, it means that in a nuclear explosion, you basically, well, you harm by a lot of things, but I think it's gonna be fatal if you close to the epicenter, if it's gonna be kinetic power, right?
So the effect is going to be very different.
Yeah.
But what is a nuclear bomb? What is it produced by? Mm-hmm. Nuclear fission. Do you get nuclear fission in a dirty bomb?
No.
What's a dirty bomb?
It's a mechanism that disperses radiation.
Radioactive materials. So it's a dirty bomb, I think it's an explosive. So that's really the difference, right? There's no chain reaction involved. There's not this huge explosion with the mushroom cloud and all that stuff. It's a very different effect, and also in magnitude it's very different. So people don't consider dirty bombs necessarily weapons of mass destruction, right? What are 2 prominent isotopes that are used for peaceful purposes but could also be used in a dirty bomb? Your guesses will probably be right. Name isotopes.
The cesium-137.
What's another one?
That's common. 9.
Mm-hmm. Strontium-90. It's another one.
Iodine?
Not in this case, because it decays so quickly. Iodine-131 decays so quickly, so it wouldn't be such a good thing. No, I have to think about it. No, I don't think it would be good. No, because you want it to stay for a very long time and contaminate the environment. And cleanup is going to be very difficult. Something else. Other isotopes you've heard of?
Iridium-183.
Yeah, good. Cobalt-60, another one. Okay. So basically, many of the isotopes that you can name, so that's why I said 2 of them, are probably going to be useful for a dirty bomb. May not be the best material for a dirty bomb, but they've got a long half-life, they stay around for a very long time. If they're difficult to get rid of by cleaning, so they're not easily dissolvable in water, Those are all good for making dirty bombs because they contaminate the environment and cause mass panic and that kind of stuff. Okay, radiation studies often divide biological effects of radiation into two main effects. What are those effects called? Long-term and short-term and long-term. Deterministic and stochastic. But I wouldn't take off marks for that necessarily because they do use some of those words. And not chronic. So deterministic and stochastic. So I said an alpha particle. What's an alpha particle?
It's something you could plug with a sheet.
We're going to get to that.
Yeah.
But what is it really? But what is it really? Is it an X-ray? We'll go through process of elimination. Is an alpha particle an X-ray?
No, helium.
What's an what's an X-ray?
Gamma ray.
What's an X-ray? You guys are just spitting. What do you think an X-ray is? It's basically a high energy light particle, right? Not as high energy as the gamma particle. It's a different process that produces X-rays, but it's still very high energy. It's very penetrating, which is why you use it for X-rays. Right? Gamma rays are even higher energy than X-rays are, right? Much higher energy, so they're even more penetrating. So you can use it for many different purposes, right? The other ones that I listed was helium nucleus. That's what an alpha particle is. It's a helium nucleus. Okay. How many protons does the helium? You guys know from chemistry? Yes. 2. Right. How many neutrons? 2. So the mass is 4.2. 4.2. So that's right. So that's the helium nucleus. Okay. And then the next one, fill in the table below. A two-stage device has two components that greatly magnify the yield of the weapon via the Teller-Ulam mechanism. You guys remember this, the Teller-Ulam mechanism? Yes? What are these components called? What is the principal fuel that generates the yield of each component? Finally, what is the type of nuclear radiation that produces the yield in each stage? In other words, please fill in the table below. So for stage 1, what's the name of the stage? Primary. The fuel material?
Plutonium.
Could be plutonium, could be uranium-235. What's the principal source of energy?
Fission.
Fission. Yeah, that's right. Stage 2, what is that called? Good. What's the fuel material? But there's also fusion. Well, now I'm giving the answer, but right, there's fusion there too. So you need a fusion fuel. Not quite. So you're thinking of a boosted weapon, right?
Yeah,
That's
sure.
tritium and deuterium, right? You're right that they're both isotopes of hydrogen. That's for a boosted weapon, and that's inside the primary, not the secondary. The secondary, the fuel's lithium deuteride, lithium hydride, but it's the hydrogen's been turned into deuterium, so it's lithium deuteride, LID, right? And that's a solid, not a gas, so it's much easier to work with as a material. And you get, the fusion energy in it. So that's the third part, is the source of energy is fusion in this case. You also have fission, part in this process, because you have the mantle around it, and so you produce all these neutrons from fusion and fission, and this causes more fission, you get more energy, and so on.
So it's fusion and fission.
Yeah, I would say fusion. It can be both, but in this case, really focused on the fusion part because the secondary is really for fusion. And so that's where I stopped, but I have some more questions. Okay? So what does a moderator do and why do we need it? So I had 4 different things, but you just tell me what it is.
Moderator to slow down the neutron.
Right. Why is that necessary? Does anybody remember?
To prevent like a fission chain reaction from going out of control.
Sorry?
To prevent a fission chain reaction, like an uncontrolled fission chain reaction.
That's not really the main point. Do you remember I had the slides where I showed that if you have, no, I'll show it to you. This is if I show it. Remember we talked about cross sections? And it's like a target. Remember I talked about that? Stay here. Right. Do you remember the cross section is basically like a target? You can think of it as being a target for neutrons in this case. And then what I wanted to show was this plot here. The neutrons are produced, the fission neutrons are produced, right? So the fission process, the neutron gets absorbed by the U-235, U-2K gets absorbed, and it splits and gives off neutrons, right? These neutrons are going to be very high energy. Here in this area here. Here, the cross-section is very small. Right? The target for the neutrons is going to be very small. So what you want to do is you want to slow that neutron down. Because as you notice, this cross-section, and when we get to the whole point, this cross-section gets much bigger. This target here, small here, but it's much bigger when you get to low energies. Right? And that means, and that's really the principal point, is that you don't need to have so much uranium-235. Otherwise, you'd have to have, 90% uranium-235 to have your power reactor. But by having this trick and moderating, right, you need to have a much smaller percentage, 3 to 5% uranium-235. You guys remember this discussion? In a moderator, you essentially turn that small target into a very big target because the cross-section changes. That's the perspective from the point of view of the neutron. Okay? So from a neutron point of view, you're turning that small dot at high energies, right, to a much bigger dot at low energies. And basically what you do with this moderation, right, neutron comes in, it hits material which are like-sized, like weight and like size. So that's why you use something like water, right? Because water is H2O, 2 hydrogens and an oxygen. So just like in billiards, remember this discussion with billiards, right? If you hit one ball and it hits another ball of the same size, same mass, it transfers all of its energy, most of its energy, to the other ball. This ball basically stops. This ball stops, and this guy continues. Okay? So you're slowing the neutrons down. That's why you use water for this purpose. So I talked about this here, right? And the point in here is that you need to have less uranium-235 because instead of it being really small, everything is about billiards, right? I hope you guys got that point, right? Everything's about probability and these little balls of neutrons going off in different places. If this splits like this, if these 2 neutrons come off here, right? If this is really small, then they're just going to pass through, or they're even going to hit a blue one, right? But because these are so big, and it's 3 to 5% uranium-235, then the chances are that this one will hit this one. Right? That's really the whole point here, and that's why you're slowing it down. And I had a picture before, I think, where I had these guys shrunk down to this size, right? In which case you will just miss them. And if you have many of them, then you have a higher probability of catching them. But if you have only 3%, then you'll just miss them. So that's why you do that, this moderation. Okay? They're called thermal neutrons, just slowing down all the way. There's different moderators, water, heavy water, and carbon. Those are the main ones that people they all have this property that they're low in atomic number because they're close to the neutron itself. Neutrons and protons are very similar, right? Similar mass, right? It's almost like a hydrogen atom, right? Proton, neutron. A hydrogen atom is basically just a proton. Hydrogen nucleus. So they're very similar. So there are these three main moderators that you should know that are used in reactors these days. And they all have different properties. Heavy water reactors are, there's many of them around the world, but primarily they're all light water reactors, using water as their, just simple water as their moderator. Okay? So the moderator is to slow the neutron down. That's the main purpose. And that allows you to have less percentage of uranium-235, essentially less enrichment in power reactors. So you can use it for that purpose. That's why it's 3 to 5%, not 90% uranium-235 that you need to have for that type of reactor. Okay. So that was the one question, extra question that I had. The other one was research reactors are not used for which purpose? And I had 4 here: generating electricity, production of radioisotopes, neutron activation analysis, or NAA, teaching and training.
First.
Yeah, answers in the question. Right? Power reactors produce electricity, generate electricity, and produce power. Okay? Research reactors are for everything else. It's for designing reactors, for making medical isotopes and industrial isotopes and these kinds of things. But it's not generally for producing power. That's not their purpose. It's for other purposes. Training is really important. Right? Things like that. Most universities, a lot of universities, at least a long time ago, had research reactors. Now a lot of them are closed because they tended to use HEU for their enrichment rather than using LEU. So they're a serious security risk because security at universities is not as high as other places. So it's a big problem. Okay, so another extra question. A sodium iodide, NaI, and germanium detector have particular drawbacks. What are they? Really, what's so special about germanium detectors? You guys remember? HPGE, I call them. High purity germanium detectors. What do you want in a good detector? Let's say we're talking about a gamma detector. You need a fingerprint? What would you want if you had a good detector? Accuracy. Right. You wanted to be able to detect the material in the first place, right? But what if you want to compare different gamma ray lines? Different gamma rays. Remember, we did this comparison with different isotopes, and you could determine what isotope is which one based on the gamma fingerprint. Remember this? Okay. This is the very last class I did. Second last. Remember this? Right? The different spectra you get. The pattern of the lines that you get, the information, the spectrum itself. The pattern tells you about what isotopes are present. And the amount, the higher the peaks are, tells you how much of the material is present. Right? And it's a way of determining what materials are present by looking at this spectra. Remember that? Like, here. Let me get to this. Remember cobalt-60? Cobalt-60 has two very distinct lines, and you don't need to know this for a test, what those lines are. But just know that these isotopes have patterns associated with them. So in the case of cobalt-60, you have a gamma ray of very specific 1173 keV, just unit of energy. Don't worry about how much it needs, but it's a unit of energy, and 1332 keV. So two very distinct lines, meaning that if I'm at a border crossing point and I'm take my detector and I measure those specific lines, I know that there's going to be a cobalt-60 source present. Right? So it's a gamma fingerprint. It's like a fingerprint material. So it's a way of telling what kind of material is present. So here I have this example. You have a picture of somebody capturing some unknown material. Right? Some unknown material has been intercepted at a border crossing point. And they're trying to find out what it is. And what happens is these particles are coming off. Right? The detectors, these are like little envelopes. And then the detector opens the envelope and checks what's the energy and the type of particle. Right? And finds that it's 1174. Here it's 1331. Here it's 1172. Here it's 1332. Here there's one which is 1336. Right? And you tally that, and you get 1170 to 1175 is 4. Right? 1330 to 1335 is 3. And then you have this straggler here, which makes no sense. Here. Right? And that's how you build up your spectrum. Right? What do I find? If I plot this, I find that in this little bucket here, between 11 and these are buckets of energy. Okay? So every particle that I collect and I measure what the energy is going to be, and I put it in the particular bucket it belongs. Okay? So this goes from 1170 to 1175, and then so on. This one 1175 to 1180, and so on, so on, so on, so on. And then 1330 to 1335, and then you guys see what I'm saying. Right? So each one is a little bucket. So I had 4 of them that were between 1170 and 1175. Oops, sorry. Okay. 4 of them were here, and there were 3 in 1330 to 1335. Right? So that means that my spectrum has kind of like a line here and a line here. As long as I have very good resolution, right? Very good resolution line detector. So I have it here and here. And this is telling me valuable information. Here, here. Right? This is telling me very valuable information because now if I wait a long time and have a very good detector, I see these 2 very distinct lines. Right? If these buckets get even thinner, I can get even more precise. You guys see what I'm saying? Right? I get even more precise. And if I have really good detectors, like H2GE, then I can do that. This is taken with an H2GE. High purity germanium detector. Right? You have very distinct lines coming from cobalt-60. So now I'm the person at the border. Right, at the border, and I'm measuring these very distinct lines here and here. Then I know for sure that there's some hidden cobalt-60 there, wherever it may be. And usually these detectors don't even necessarily show you the lines, because these are all built in libraries. But the detector knows itself, and it does the analysis of what's present. It will say cobalt-60 is present, because it did this analysis and looked at whether these lines are present. So you have a lot of information there. From the physics, from the nuclear physics, we know that when a cobalt-60 decays, it will produce 1173 keV gamma and a 1332 keV gamma. Not only that, you also know the proportion of them. How many there should be with respect to it. Right? So you know if they're faking, because maybe they're, they pretended to be some other isotopes. another isotope. It's important for verification. So cobalt-60 has this gamma fingerprint that looks like this, and this allows us to determine whether it's cobalt-60. HEU and LEU have a similar fingerprint that allows you to determine what the enrichment is and so on. And so this is really important. And the difference between HPGE and sodium iodide detectors is that HPGE gives you this, has a very excellent resolution, has an extremely good resolution. So it really looks like lines. Whereas if it's a bad resolution, just like a bad resolution picture, right, it looks like this. That's in my slides, you guys can see there. Right. If you have HPGE, it looks like this. If it's sodium iodide detector, which I have upstairs, it looks more like this. So, if there's another peak hidden here, another line hidden there, I might not see it. Okay. So what do you want to have for a good gamma detector? Resolution. You want the resolution to be really good so that you can actually distinguish these lines in a very powerful way. Right. The problem with HPGE, I have the sodium iodide detector upstairs, and the spectrum looks like this. Not as nice as these nice lines, right? I don't need to cool it or anything like this. It's just very nice. I can just turn on the detector, go into the field, take spectra if I want to. It's very easy to do. But with HPGE, I need to cool it with liquid nitrogen. And they have now sophisticated techniques that they can have cooling systems where basically refrigerators where you can cool them, but you do need to cool them, and that's an added problem with HPGE. You need to constantly cool the detector. It's one of the negatives. Okay. So, sodium iodide detectors have low resolution, whereas HPGE or high purity germanium detectors or germanium detectors themselves have a much, much better resolution. You get these very sharp lines. That's really what my point was. So I have another question here, which is, according to Steve Feder et al., and I give the reference here, about 4 kilograms plutonium is required for a bomb. How does this compare to one significant quantity of plutonium? So, according to Steve Feder, the physicist at University of Maryland, former advisor to President Obama, he estimated that the amount of plutonium that you would need, weapon-grade plutonium, I believe it is, to have a nuclear weapon is about 4 kilograms. How does that compare to a significant quantity? Right, it's half of that.
But it's probably referring to like an advanced production.
Absolutely, absolutely. But it does make an important point, is that the significant quantity tends to overestimate the amount that you actually need to make a nuclear weapon. And that's really the point I was trying to make. So, nuclear spent fuel is a mix of isotopes, plutonium and uranium that has not fissioned yet. What is the process called that removes plutonium from the spent fuel? This process is used to make plutonium-based fuel, but is also used to produce fissile material for nuclear weapons.
Reprocessing?
Yes, reprocessing.
Can you say that question again? Sorry.
Okay, so nuclear spent fuel is a mix of isotopes, right? Plutonium, uranium that's not fissioned yet, and other things too. What is the process called that removes the plutonium from the spent fuel? Reprocessing. Yes. Nuclear reprocessing or just reprocessing, both are fine. Not, yeah. Okay. Explain, this is question 26. Explain what could happen if the reactor is not cooled promptly and the coolant boils away in the reactor. This is what happened in Fukushima. Sorry?
Bad things happen.
Bad things
Yeah.
Happen last now.
Yeah.
Was your question if the reactor is not cooled?
The question is worse than that. It's not cooled properly and the coolant boils away. So can you be a bit more specific? think I went through
So you no longer have a cooling agent, therefore, the material inside the reactors continues to burn and eventually will basically get to the fusion point of whatever metal is containing it, whatever material you have it, it's gonna melt it down, and therefore all this material is gonna go, like, escape the boundary of your reactor basically, so they're gonna go.
good enough on that side, yes. Very good. Right, so basically the material itself gets hotter and hotter, starts essentially burning itself. Materials start evolving from it, and then at one point gets so hot it will start to melt and sort of become a little pool at the bottom of your reactor. And be in a shape that you can't predict. So you don't really know what's going to happen, how it's going to behave.
In the video about Chernobyl, they were showing exactly that, but the material was basically like, imagine you have a pool of acid in a ship, like it's gonna continue to go down, and if it hits your water table down there, and it's gonna contaminate the whole thing. So in Chernobyl, they were trying to kind of build a structure below it that would
Prevent
prevent,
it,
yeah,
yeah.
that was a big issue.
Exactly. Now, here's a good one. So follow me closely. I have two radioactive sources sitting on the table. One is a beta source, and the other is an alpha source. Assuming that both sources have essentially the same radioactivity, this is the quantity which is measured in units of becquerel, curie, or whatever, right? If, one, I decide to pick up the sources, I decide to pick up the sources with my hand, which of the two sources will be most damaging to my hand? Okay, good. I decide to eat both sources. Don't try this at home. Which source will be most damaging to me and why?
Alpha.
Why? Doesn't mean I would ask the same question. That's not a trick question if I ask it, it's the same answer. Why is an alpha so dangerous?
When it decays inside you, like the other sort of
The alpha emitter?
yeah.
And what does it do? What's the alpha emitter do?
I think it confuses the body system, and the body thinks some other, either calcium or one other potassium.
You think about strontium and that stuff. But
Okay.
that's not really what I'm really looking for. The main thing you have to think of an alpha particle, and I think I showed this before. It's a soft tissue, right? Inside it's soft tissues and things where it can do a lot of damage. You have to think of it this way. It's kind of like, I really think I showed this before. If you have soft tissue, you have an alpha particle. You can think of an alpha particle like a bus or a truck slamming into things. It doesn't go very far, but it has a lot more punch than a beta particle. A beta particle will just damage as it goes through. They will just pass right through. Not deposits, and that's the key, not deposit so much energy as a function of path length. Okay? So a beta particle will go through, but an alpha particle will stop here and deposit all of its energy right at the last point. So the way I always looked at this, and I think I used this as an example in class, it's kind of like taking a needle, poking it in soft tissue, and having a little explosion at the end. That's the damage an alpha particle does. And the way you can think of this, I mean, this is the actual physical picture, is if you look at the energy deposited versus distance in the tissue, it goes something like this. So all the energy is deposited when it poked as much as it goes as far as it can. You see what I'm saying? So it's like a needle that pokes in, and at the very point when it's losing, losing its speed essentially, and it's depositing all its energy. That's why alpha particles do so much damage. Right? They don't just simply pass through like this guy does, like a beta does, and just damage the molecules as it passes through. It damages things much more concentrated. It's like a little explosion poking with, think of it this way, like a needle poking and then a little explosion at the end of the needle. That's a damage that non-particle does. That's why it's so dangerous.
So in terms of effective damage is what happens.
Yeah.
Be more specific.
So you get more.
Like the amount of damage that can happen, like, you know,
So in this case, you could produce a lot more damage because you're concentrating on the damage you're producing is to the energy that you're depositing in the material. That's really what dose is. So the dose that you're delivering is much more localized, and so you can produce much more damage. Right? Much more than betas or gammas or these kinds of particles. Of course, it depends on how many gammas you have and how many betas you have. But here the comparison was, basically equal activity or something like this. Okay, so that's really what I wanted to say, is that it's very different in terms of how damaging betas are versus alpha particles are. So don't swallow alpha sources.